the factor theorem. So, we've got a few questions to work through here. We'll see how we go with timing, but the exercise is short. Okay, so it's a short exercise, so we'll set that for sort of homework tonight. Let's get straight into it. So, for any polynomial, if k is a 0, that means if it's a root, if it's one of the x-intercepts, then x take k is a factor. Now, just to be very precise, what we mean by factor is if you pull it out the front, there's no remainder. If you divide by it, there's no remainder left over. That's what a factor means. Okay, so we have this polynomial. It's x to the 3, take 7x squared plus ax take 9. And we're told x take 3 is a factor. If x take 3 is a factor, what it means is p of 3 is 0. Okay? So we put the number 3 into this equation. 3 to the 3 takes 7 times 3 squared, plus 3a take away 9. We have 27, take 7 times 9. Alright, so we'll just keep tapping away at this. 9, 7, 63. So that would be minus 72. And minus 45. So we'll have 3a is 45 and we'll have a is 15.
That's a late mental.
Alright, so that's one. Let's go to question 2 then. The other marker. Any questions about that one? Okay, so in question 2, we have the polynomial. Oh, this one's not better, this one's worse. Z to the 3, z squared, 3 take 5k multiplied by z, plus k squared plus 3. Okay, that's our polynomial. Find k and all the possible roots given that z take 1 is a factor. Okay, so if z take 1 is a factor, then p of 1 equals 0. Alright, that's the factor theorem. So then we put the number 1 where the z's are. We'll have 1 take 1 plus 3 take 5k plus k squared plus 3. Okay, this has given us a quadratic. 1 take 1 will cancel, so we're left with 3 take 5k plus k squared plus 3. In the next step, I'm going to collect these like terms. So where we have 3 and 3, and I'm going to put the k squared first. So I've got k squared, take 5k plus 6. Okay, factorise that. K take 3, k take 2. Okay, minus 3 times minus 2 is positive 6, minus 3 plus minus 2 is minus 5. Apply the null factor law. Okay, so we've determined 2 possible values of k. So that's the first part of it done. Find k, alright, and all possible roots of this polynomial. Alright, so we've got 2 circumstances we need to investigate. We need to first investigate if k is 3, and then we need to investigate if k is 2. So let's go first if k is 3. Okay, if k is 3, the polynomial that we have then, alright, I'm going to substitute 3 for k in here and here. So the polynomial that we have is z to the 3, take z squared, plus, and I have 3, take away 5 lots of k. That's going to be 3 take 15. Alright, because k is 3 in this circumstance, that's going to be minus 12. And then plus 3 squared, that'll be plus 9, plus 3, plus 12. Alright, so if k is 3, this is the polynomial that results. Now, if this is the polynomial, we're asked to find all of the roots of this polynomial. Now, we know from the first part, z take 1 is a factor. So that means z take 1 multiplied by some quadratic will equal this polynomial above.
Just tying everything in together.
Okay, so that's what we've sort of covered over in 2a and 2b. If k is 3, this is the polynomial. We know this is one of the factors of the polynomial. So in order to find the other roots, we need to identify what's this quadratic factor of the polynomial. So if we're to perform the expansion, you can do it if you want to, all right? But you can actually start to look for shortcuts in here, all right? So I know there's no number out the front there because I know the leading coefficient is 1, okay? So I know that there's no a there. I also know that minus 1 times c has to equal positive 12. That's the constant term, right? Minus 1 times c has to equal 12. So straight away, I can look at that and see what my value of c is. See? All right, so we have the value of c is 12, and then we need to determine the value of b. Now, it can be helpful to expand, and if you're going to get a little bit lost here, I do encourage you to expand. But the value of b, all right, is here, and it's going to affect, we can get it from two possible ways, right? From the z squared term or from the z term. Either's going to be fine. So if you prefer expand, but let me just try and explain a little bit of reasoning here. Okay, minus 1 times z squared will give us minus z squared. And z times bz will give us plus bz squared. Okay, and those together will combine to give us the z squared term. They're the only two that we would add together if we perform the expansion. That would give us the z squared term. And when I add them together, so if I have b take away 1 of z squared, okay, 1 lot of b squared, 1 lot of bz squared, take away 1 lot of z squared, b take 1 of z squared, it has to equal minus 1. Okay? So you can perform the expansion, right? This might be a faster way to think of it if you can see it. So this means b has to be, so we have b take 1 is minus 1, b has to be 0. Alright? Which means that this quadratic factor is, so that the polynomial, if I write it out here, it's z take 1 multiplied by z squared, and then that should say minus, z squared take 12. Okay, the value of c is minus 12. Alright, the value of b is 0. So we're going from there, z take 1, that's there. Here's the quadratic part, z squared take 12.
This is just k equals 3.
This is just k equals 3. Yeah, so there's another circumstance, isn't it? We'll just go through the first one. So then we make it equal to 0. Apply the null factor law. So this gives you z is plus or minus the square root of 12. And this gives you z is 1. So we've got 3 roots to that cube. Just on the plus or minus root 12, you know, that's root 4 times 3, which is root 4 times root 3, which is plus or minus 2 root 3. So that and that are the same way of representing, are different ways of representing the same answer. We'll accept that you can simplify it. You type that in your calculator, this is what it will spit out. Okay, so does everyone see? Let's just explain how we did that so far. First, we identified the value of k by using the factor theorem. The factor theorem says if it's a factor, if z take 1 is a factor, then p of 1 is 0. So we put p of 1 in, and we know it's equal to 0. We come up with an equation for k. We solve for k. We've got 2 possible solutions. We've investigated this case. We said if k is 3, this is the resultant polynomial. All right. Now, if I want to know the roots, I know that it can be multiplied by some linear factor. Okay. I know that this is a factor, I know this has to be some quadratic factor. All right, and then I identify the values of C and B, either using the expansion method or, you know, if you can see it, you can get it, you get values of C and B. So that means this is one way of presenting the polynomial. All right, apply the null factor law, and there's your possible roots. Okay, so that's quite long, right? I'll leave it up to you guys in a moment to have a go at finding the roots when K is 2. Okay, so you put 2 where K is, and follow through. All right. Now, I reckon we might stop there. This is an exam question, a previous exam question, and it's a good summary of the remainder theorem and the factor theorem and so forth. So I reckon it might be a good one to recap with tomorrow. All right, so I'll stop there. I know what I'm doing. All right, so this question's an old exam question, okay? And so this is a good point for us to sort of recap what we've done yesterday, where we talked about the remainder theorem and we talked about the factor theorem. So we'll start, we've got P of x is a cubic polynomial, so we know it's x to the power of 3 of some variety. When P of x is divided by x take 1, the remainder is 35. Okay, so this means, I've abstracted that information, it means P of 1 will equal 35. When it's divided by x plus 2, the remainder is 80. So P of minus 2, okay, the root of x plus 2 will give us the 80. So they're the two pieces of information we're going to use first. And this is what we're told. Find A and B given P of x is equal to this. Now, in question 7 that we were talking about yesterday, it had these same properties, only it didn't give you this part here. P of x is a cubic. We know that Q of x times the divisor. Okay, we've got whatever the divisor is. We're going to be left over with some linear remainder because we're dividing it by a quadratic cube. Okay, find the values of A and B. So all we're doing first is plugging this information into here in order to determine what's the value of A and what's the value of B. So I'll start with, when x is 1, P of 1 is 35. So let's put that in. We're going to have 35 where the P of x is, and we'll have 1 where the x is. So it should be that we have 1 plus 1 is 2, 2 take 2 is 0, so that's going to 0, okay? And then Q of 1, we don't know what the Q function is, but Q times 0 is going to be 0, so that whole part's 0. And then so we're just left with A plus B equals 35. All right, and so this is going to be one of those simultaneous equation ones that we'll solve in a moment. All right, A plus B is 35. Let's use the other piece of information. We have when x is minus 2, P of minus 2 is 80. All right, when we plug minus 2 in, the function equals 80. So we'll put 80 where the P of x is. And we'll put minus 2 where the x is. Make sure when you put the minus 2 in, it's minus 2 in brackets, squared. Okay, so that's going to give us, again, this component's going to be 0. So we have 4, take 2, take 2, that whole thing is 0, so that whole thing is 0. So we're just left with minus 2a plus b equals 80. We've got those two equations there, and we're familiar with substitution. I'm going to keep using elimination. That's what's going to pop up later when we're doing vectors. So we have equation 1 and equation 2, and we can see we've got the same value of b. So if I do equation 1, take equation 2, it's going to eliminate b, hence method of elimination. 1 take away 2, let's state what we have. We'll have a take away minus 2a. A take away minus 2a, that's going to be a plus 2a, 3a. B take away b will cancel, and then 35 take 80 will give you negative 45. This follows through for a is minus 15. Okay, if A is negative 15, all right, negative 15 plus B is 35. B has to be 50. All right, by adding 15 to both sides. So we've determined the value of A and we've determined the value of B. Okay, so that means the polynomial that we have here, so that's our answer to part A. The polynomial that we have here then, that we'll use in part B, takes this form, doesn't it? We have P of x is equal to Q of x, multiplied by x squared plus x take 2, plus, and we have A is minus 15, minus 15x plus 50. All right, so I'm just going straight from here. I've copied everything down, except I've plugged in the A value and I've plugged in the B value. Okay, so part A is remainder theorem, we're familiar with it. Part B says, if x take 2 is a factor of P of x, show that Q of 2 equals minus 5. So if x take 2 is a factor, what this means is P of 2 is equal to 0. That's what it means. That's the factor theorem. Okay? If it's a factor, when you plug in the solution to that factor, it will equal 0. So let's type that in. We've got P of 2, which will be Q of 2 times 2 squared plus 2. Take 2. Take 15 times 2 plus 50. I'm just typing it all in, plugging the 2 where the x is. And we're told if it's a factor, well, by the factor theorem, it's equal to 0. Now let's just process this a little bit. So we have Q of 2 out the front here. We're multiplying that by 4 plus 2 take 2. That's just going to be times 4. So that means, I'll put times 4 so it doesn't look like it. Take away 30 plus 50 equals 0. So we've plugged it in. This is what we've arrived at, and maybe now's a good time to go, hang on, what am I doing here again? What's the question say? Show that Q of 2 is minus 5. It wants you to get this component by itself. Remember, this is not Q times 2, it's the function Q, the quotient of the x value 2. So what we have, all right, I'll just do it in a couple more steps. We've got 4 times Q of 2, all right, that's what this means. We've got 4 lots of the function Q of 2, minus 30 plus 50, that gives you positive 20. And we're just solving this for Q of 2. We'll subtract 20 from both sides, and then divide both sides by 4. There we are. Okay, so we've got Q of 2 is minus 5, we've shown that that's the case. We'll need a little bit more space, so I might just clear off part A for now. Okay, given the leading coefficient of P of x is 1, show that Q of x equals x takes 7. Okay, so the P of x is a polynomial, right? And it's a cubic polynomial. So that means it's of the form ax to the 3 plus bx squared plus cx plus d, all right? That's what it has. Now we're told the leading coefficient is 1. So what does that mean the value of a is?
1.
1. A is 1, okay? So that means, all right, over here we have a quadratic, all right? And so what do I have to multiply a quadratic by to get a cubic?
X.
X. This has to be a linear factor. Q of x is linear, all right? So Q of x must be linear. All right, it must be a linear factor because a linear times a quadratic will result in a cubic. So that means Q of x, to start with, it has this form, right? It's ax plus b. And I'm aware we've used a and b above. So maybe we should use something different. Should we use mx plus c for the equation of a line? Okay. Q of x must be a linear factor. All right, so the value of m, though, has to be 1. Because the leading coefficient here is 1, x to the 3, and mx, all right, when we multiply this out, I'll write the whole thing out, x squared plus x take 2. When we multiply mx by x squared, it must equal 1 lot of x to the power of 3, okay? Which means m must be 1. And so the linear factor that we're left with, what we arrive at, is this x plus c. All right, we've got x plus c. Okay, the leading coefficient of x is 1. Show that q of x is equal to x take 7. So p of x is a cubic, we've established that. A is 1, q of 2 is 5. Okay. So if you think back to the previous part, we established q of 2 equals 5. Now at the moment, this is what we have for q of x, right? Remember, this is our q of x part. All right, we've derived it here, q of x. So q of x is x plus c. All right, I'll make that q of x is x plus c. And we have q of 2 is equal to minus 5. So that means when I put the number 2 into here, it's going to equal minus 5. So 2 plus c equals minus 5. And so we get c is minus 7. And if c is minus 7, therefore q of x is x take 7. All right, so is everyone okay with that argument? There's a little bit of implication up here, where we have to think about, okay, this has to be a linear, because a linear times a quadratic will result in the cubic. This has to be 1, because the leading number out the front is 1, so we're able to get rid of that. And then we've just got, this is the q of x function, and we know from before that q of 2 is minus 5, so we solve through for the unknown, we've found the q of x part by itself. Part D, hence find p of x in expanded form. So let's write out what we have for p of x at the moment then. We have p of x is equal to q of x multiplied by the quadratic factor there, the divisor, x squared plus x take 2. And then we have plus ax plus b, was b 50?
Yeah.
Yep. All right, so all we're going to do is expand this completely and collect like terms. So I'm going to perform this expansion first, and I'm going to recap for us. When we expand this, we want to stagger them so that we can collect the like terms vertically. So I'm going x times x squared, x to the 3, x times x, okay, will give me positive x squared, and then x times minus 2 will give me minus 2 lots of x. Okay, then we'll multiply the minus 7 through. All right, minus 7 times x squared, minus 7x squared. And we put that right below the x squared term. Minus 7 times x will be minus 7x. And then minus 7 times minus 2 will be positive 14. Okay, so that's what we get when we expand this part of it, right? And then we've got these two other terms at the end that we're going to add on. So I'm just going to whack them right below where we're combining them. So this is an x term, it adds up with the x's. This is a constant term, it adds up with the other constant term. So that means our resultant polynomial, p of x, is x to the 3. Now we've got one lot of x squared, take 7 lots. That will be minus 6x squared. Minus 2 take 7 is minus 9. All right. Take away 15 is minus 24. And then 14 and 50 is 64. That is our cubic polynomial that we arrive at using the remainder theorem, using the factor theorem. What an absolutely gorgeous question. All right, so let's just proceed with where we're up to. I anticipate we'll be having a bit of a go at the factor theorem today, just applying what we did in part B there. All right, so I'll stop there. Any questions?